Hello, my name is Dr. Jake Herndon. I'm a mathematician and a tutor from Chicago. This video is all about the Klein Group. So, should you watch this? You should, if you're studying abstract algebra and you've already seen a little group theory, so you know what the definition of a group is and you know what the definition of an isomorphism is, and you want to learn more examples of some important groups. So this video is about one group in particular, called the Klein group. Also, sometimes it's called the Klein 4 group. It's one of the first groups that people encounter when they're studying group theory, and there are many ways to think about this group. So I'm going to talk about a few different ways to think about the Klein group. First, let me just remind you a little bit about group theory. So a group is a set with a binary operation that's closed, associative, has an identity, and has inverses. A group homomorphism is a function between groups that preserves the operation. And a group isomorphism is a group homomorphism that is a bijection of the underlying sets. And two groups are isomorphic if there is an isomorphism between them. Isomorphic groups are considered to be the same group. The isomorphism is just relabeling the elements, but essentially the operation is the same operation. So I'm expecting you already know all that. It's just some background in case you forgot. All right, on to the Klein group. So whenever you're defining a group, probably the most direct way to do that is just say what the multiplication table looks like. So let K be this 4-element set. It contains 1, A, B, and C. And consider this multiplication table. So here are a few observations about this table. 1 is an identity element, so the top row says if you multiply by 1 on the left, you don't change the thing you're multiplying. And the leftmost column says if you multiply by 1 on the right, you just get the same thing back. A times 1 is equal to A. Every element is its own inverse, so you can see that by looking along the diagonal. It's all ones, so A times A is 1, B times B is 1. And the product of any two non-identity elements is the third non-identity element. So A times B is equal to C, B times C is equal to A, and C times A is equal to. And the Klein group is K with the binary operation defined by this table. And if I'm being honest, I should let you know, the operation is associative, but I'm not checking that here. So you can believe me if you want, or you can check it yourself. All right, moving on. So one place where the Klein group shows up naturally is when you are studying rectangles. Here is a rectangle. Any rectangle has 3 non-trivial symmetries. So one thing you can do with the rectangle is you can flip it over the horizontal axis. Another thing you can do with the rectangle is you can flip it over the vertical axis. And another thing you can do with the rectangle is rotate 180 degrees. So let's call these symmetries F sub H for flip over horizontal, F sub V for flip over vertical, and R for rotation. And let's call the trivial symmetry I. So if you just leave the rectangle exactly how it is, that is I. So if you take these 4 symmetries and put them in a set, you get a set with 4 elements, and it's a group if you give it the operation of composition. So the operation of composition just says do one symmetry and then do the other. Whatever the net result is, whatever symmetry you get after doing them both, that's the product of those 2 symmetries. You can study this group by playing with a note card, and everyone should do this at least once. So if you haven't done this before, I'm going to do it with you right now. So here is my rectangle. If I don't do anything, that's the trivial symmetry I. If I flip over the horizontal axis, that is f sub h, back to the start. If I flip over the vertical axis, that's f sub v, back to how it was. And if I rotate 180 degrees, that's r. So now what I wanted to point out here is if you do any symmetry twice in a row, you end up back where you started. That's saying that every symmetry is its own inverse. So if you flip over the vertical and then flip over the vertical again, you end up back at the identity. Same thing if you rotate and then rotate again, you're back where you started. And same thing with the other flip. Another thing to point out is if you do two of the non-trivial symmetries back to back, you get the third non-trivial symmetry. So if you flip over the vertical and then flip over the horizontal, you get the rotation. Get back here. If you do the rotation and then flip over the horizontal, you get the vertical flip. So this was the thing from the multiplication table on the last slide. A times B is equal to C. B times C is equal to A. You compose any of the two non-trivial symmetries, you get the third non-trivial symmetry. So if you've never done that before, now you have. So the main point here is this group is the Klein group. It's the exact same group as the one whose multiplication table I wrote down on the last page. The only difference is I've relabeled the elements. So this group, things are called I, FH, FV, and R. And on the last slide, I called the elements 1A, B, and C. So here's a question about rectangles. How should you flip your mattress if you want to wear it out evenly? And the answer to that is you should flip it in the fall and spin it in the spring. Point here is that only one kind of flip is actually needed. So here's your mattress and you want to wear it out evenly. So you can do the horizontal flip in the fall and then the 180 spin in the spring. Next time fall comes around, do the same horizontal flip. Then next time spring comes around, do the 180 rotation. And if you do that, you will hit all possible orientations of your mattress. So, why do I know this? Well, not only am I a mathematician, but I used to work in a futon store back when I was an undergrad. So shout out to Right on Futon. Every now and then people would come into the store and they would ask, what's the best way to flip my mattress? And I would say, you can use the Klein group to do this. And then sometimes they would appreciate that and sometimes they wouldn't care at all. But if anyone ever tells you abstract algebra is not useful, you can tell them it has applications to mattress flipping, so there's at least one use for it. All right, next way to think about the Klein group. It's the smallest non-cyclic group. So you've probably already seen these definitions, but I'll just remind you what they are. The order of a group is the cardinality of its underlying set. So if the group is finite, that's just a natural number. It's the number of elements in the group. And a group is cyclic if there is some gamma in the group, some group element, so that every other element of the group is a power of gamma. Another way to say that is a group is cyclic if it has a single generator. So the Klein group is the smallest group that is not cyclic. So to spell out what this means, if you want to prove this, you'd have to show that all groups of orders 1, 2, and 3 are cyclic. And if you've got a group of order 4, it's either cyclic or it's isomorphic to the Klein group. So there's a bunch of theorems about finite groups that make it easier to prove this. I think you can prove it by hand though. So what I mean is you can draw like a 4x4 multiplication table and don't fill it in yet. But But then you can start filling it in, and if you use some properties about groups, you'll be forced to fill it in one of two ways. It'll either be cyclic or it'll be the Klein group. So I can show you more about that if you're interested, but I'm going to leave it out of this video. All right, moving on. The Klein group is a product group, so I'll tell you more about that. Let Z mod 2Z denote the additive group of integers mod 2. So the two elements of Z mod 2Z are the equivalence class of 0 and the equivalence class of 1 mod 2, also known as the even numbers and odd numbers. The equivalence class of 0 is the identity elements, and 1 plus 1 mod 2 is equal to 0 mod 2. The direct product of Z mod 2Z with itself is the group that contains these four elements. So there's one element that's got 0 in both coordinates. There's another element that's got 0 in the first, 1 in the second. And then there's another that's got 1 in the first, 0 in the second. And then there's another that's got 1 in the first and 1 in the second. And the group operation here is just component-wise addition. So, for example, if you add this element to this element, you add the first coordinates together. You add 0 plus 1 and you get 1. And you add the second coordinates together. So you add 1 and 0 and you get 1. So if you add two of the non-trivial elements together, you get the third. What I wanted to show you there. And then also if you add an element to itself, you get the trivial element. So this element plus itself gives you 0 in both coordinates. And you can just check, if you add any of these elements to itself, you get 0 in both coordinates. This product group is another way to think about the Klein group. All right, let me close out the video with a few exercises about the Klein group. So the first exercise is to verify associativity from the multiplication table. At the start of the video, I wrote out a 4x4 multiplication table. I told you it was a group operation. Part of that's associativity, but I didn't actually check that it was associative. So remember that associativity says that for every x, y, and z in the group, if you multiply x times y times z like this, you get the same answer as if you multiply x times y times z like this. So to check associativity, there's a bunch of cases. There's 4 options for x, 4 options for y, and 4 options for z. So there's 4 times 4 times 4 cases. Sounds like a lot of cases, but I'm sure you can do it if you're interested. Next exercise. Check that all of the different descriptions of the Klein group in the video are actually isomorphic. So I'm claiming they are, but maybe you'd like to check for yourself. Third exercise. Show that any bijection from K2 itself, which fixes the identity, must be a group isomorphism. So in other words, the group K can't really see the difference between its non-trivial elements. When you write it out as like a mattress flipping group, 2 of the elements seem similar and 1 of the elements seems kind of different. It seems like the 2 flips are like twins and then the rotation is like a step sibling, but that's not actually true. You can exchange any 2 elements and get a group isomorphism, and exchange all 3 of them. You can do that too. So that's the essence of question 3. For exercise 4, investigate the sequence generated by flip in the fall, spin in the spring. So I'm saying A is flip and B is spin. So if you flip, spin, and then flip, spin, you get this sequence. And my question is, why does this actually wear your mattress evenly? Can you say something about the way A, B, and C show up in this sequence? And last question. So this is if you know about symmetry groups and normal subgroups. Show that the symmetry group on 4 elements contains both normal and non-normal subgroups, which are isomorphic to K. And that is all I have to say. So thanks for watching. I tutor online, so if you're looking for a math tutor, you can contact me through my website. It's herndonmathservices.com. And if you like this kind of video and you want me to make more, let me know. I might do that. And happy studies. Bye.